Engineering 305, Chapter 5, Problem 43. The assembly shown in the figure, 543, consists of a steel bar with known properties, Young's modulus, and area. A rigid bearing plate C, oh, there's always our key, right? Something rigid, that's securely fastened to bar A, and a bronze bar B. So I got steel up above, and then bronze down below. Bronze is B, that's good. There's a clearance, however, this time in our system that exists between the bearing plate C and the bronze B underneath before the assembly plate is loaded. After it's loaded with 95 kips evenly across the plate, after it's loaded, find the normal stress in A and B and the vertical displacement of bearing plate C. All right. Right, it's going to kind of follow our normal format. I'm going to get this up and out of my way a little bit. Oh, I'm going to need the material properties, but, well, we'll just fight through it. What are we trying to find? We're trying to find our stresses. So let's start. Our stresses in the steel are equal to the force of the steel over the area of the steel. Our stress in the bronze, brass, bronze is equal to the force in the bronze over the area of the bronze. And then I have my two deflection equations. The deflection of the steel is equal to the force in the steel, length of the steel, area of the steel, Young's modulus for the steel. The deflection in the bronze is equal to the force in the bronze, the length of the bronze divided by the area of the bronze, and the Young's modulus for the bronze. Now we get to what I'll say is the creative part. It takes a little more of something going on. There is a force relationship that we have to come up with. So the force relationship comes from a free body diagram on the plate. Okay, and that's actually a hard one because there's two situations. There's a situation where I have this and I have a load. I'm going to do my load in red. I have my load there and I have a reaction force there. And this is the situation initially where they haven't come into contact. Okay. I also have a situation, draw it in black, where now they've come into contact, and I've got that pulling up and that pushing up. Right? Now, notice I drew, starting out right away, that I drew with the wrong. I drew it in the wrong direction. I've been saying, yeah, focus on tension, focus on. Yeah, okay, so let's clean that up. And I'm going to say I expect that to be negative, but that makes the world go round in a proper orientation. So that's all good. It's all good. Okay. Now I have to assume, I have to pick one of those two. I have to pick. And I am going to pick this one because if I find out that the math doesn't work out, that I can't solve it, it's because that is the wrong one. And then I can go right back up to this equation and say, I know what the force is, I know what the stress is, because all the weight is going into the steel. So unless this works out, then, you know, or the other way, I could pick this one and realize I could calculate that delta, which is equal to Fs over F, force in the steel, length of the steel over area, Young's modulus. I'm going to figure out that that's greater than 15 thousandths of an inch, which is that gap. And that's not a bad thing to do. Here, let's try that. Delta in the steel is equal to the force in the steel. Well, I know the force in the steel now. I know the force in the steel. It's taking the whole load, 95 kip, times the length of the steel. Well, it's given as 6 feet in the picture. 6 feet divided by, and now I already have a, yeah, we're going to run into a little problem here. Area of the steel is 1.25 inches squared. 1.25 inches squared. I don't want to do that. I want to do 1.25 inches squared. And the Young's modulus for steel is 30 E6, right? It's 30,000 KSI, so that's 30 E6 PSI. Now, this is in feet. The 6, I point, and you guys can't see where I'm pointing, but I point at the 6 feet and go, yeah, I can't do that. That's got the wrong units. So let me get rid of 6 feet and put in 72 inches, 6 times 12. And now I've just got it in there right away. Let's calculate that a second. And I calculated 0.182 inches. So that's big. That's a big deflection. But it's clearly going to close the gap. So this situation is not correct. The force is only hanging on the steel. We're doing the second situation. So with everything now in the right direction. So let's go solve that free body diagram. I guess I should put a coordinate system on here. X, Y. I'm going to do some of the forces in the Y. Are equal to the force in the steel is acting up minus 95 kips acting down minus the force in the bronze equal to 0. So Fs minus Fb is equal to 95 kip. Now, if you're looking at that and you're going, that's not a minus, they're both acting up, I know but that's the way we drew our sign. So I expect the force in the bronze to be negative, and then it would be the force in the steel plus the force in the bronze is equal to 95. But I expect it to be negative. I'm following my sign convention. That's what I got to do. Okay, I need one more equation, right? And that one more equation is now related to the deflections. It's related to what I've been calling the kinematics of the situation. How does that move? Well, here's the equation that I'm going to propose. The deflection of the steel is equal to the deflection of the bronze. Oh, I got to get my signs right. So let's see if I can draw right on here. Can I put a coordinate system here? That's my Y direction. I don't know what that other little thing got in there is. That's my Y direction. So the deflection of the steel downward so the negative deflection of the steel, go back to blue here, is equal to the deflection of the bronze. Oh, I got it. Hold on one sec. All right, ready? Here's the fun. Since those have opposite signs in terms of what a positive deflection is, the deflection in A plus 15 thousandths minus the deflection in B is equal to 0. So if the deflection in A is 0, I add 15 thousandths, and that's the deflection in B is a minus 15 thousandths in order for them to close the gap. That doesn't happen. If the deflection in A is 15 thousandths, that would be down plus 15 thousandths. Then the deflection of, nope, it's not right. That's why I'm struggling with this one. And this is where there's some creativity. This is a bugger. And now I screwed up my video. Yeah, it's easier and it's harder than I think. So basically, the deflection of A minus 15 thousandths is equal to the deflection of B, but B is now goes in the other direction, so it's negative, is equal to a negative delta B. Okay, so let's start thinking about this. If A moves 15 thousandths, then I subtract 15, and the deflection of B is, and the deflection of the bronze is 0. If the steel goes 30 thousandths down, then I subtract 15, and it's 15 thousandths down, and that means B has a negative, B is a negative 15 thousandths, and that would be correct. It would shrink by 15 thousandths. So I got my signs right, got it good. I'm good. I'm ready to rock and roll forward. Now I can start working and rearranging and doing all the math. So the first thing I'm going to do is I'm going to use my two Flay equations and substitute them in here for the deltas. So, and I don't know if this is the right approach. It's just what I'm doing. There might be a better approach, but it's the force in the steel, or the force. Did I call it FA? I call it FS. This should be force steel. FS, length of the steel, over area of the steel, Young's modulus for the steel, minus 0.015, and I'm going to move it to the other side because it's all going to make this easier. This is a plus delta B, which is force in the bronze, length of the bronze, divided by area of the bronze, Young's modulus for the bronze, is equal to 0. Now I'm going with, I'm going to rearrange. I'm going to replace, I'm going to go to this equation and rearrange it so that the force in the bronze is equal to force in the steel minus 95 kip. Okay, so now I've got force in the steel, length of the steel, over area of the steel, Young's modulus for the steel. I'm moving the 15th, I'm back working on this equation. I'm going to move the 15 thousandths to the other side. But here I've got force of the bronze. I'm substituting in force of the steel minus 95 kip. Length of the steel, length of the bronze, area of the bronze, Young's modulus for the bronze, is equal to positive 0.015 because I moved it to the other side. Now I can rearrange. Actually, everything is known except for the force in the steel, right? I know area of the steel, Young's modulus for steel, length of steel, area of the bronze, length. The only thing left, the only unknowns there are this force in the steel. So I can plug in all the numbers and solve. It's going to look like, it looks like that. I just substituted in for the length. So force of the steel, 72 times 72 inches, 1.25 inches squared, 30 MSI, right? Boom, 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 punch that in. I separated force of the steel from the 95, distributed that. Now I'm going to punch in numbers, and what I'm going to get is, I'm going to get force of the steel times a coefficient is equal to 0.015 minus that constant, and then I can solve it. All right, it'll look like, so then if I know the force in the steel, the force in the bronze is 95 kips, minus the force in the steel, right? Is that my equation, or did I just derive that in my head? Force of the bronze equal force of the steel minus 95. Whew. So, okay, I got my sign wrong here, which is important. I want to go back up to this equation. Force of the bronze. Let's, I'd do a snip, but I forget how. Force of the bronze equals force in the steel minus 95 kip. Now, the reason I want to do that, because I've been following sign convention, force of steel is 23,732 minus 95,000 is equal to 71,000. Well, a negative, right? 71,268 kips. Negative, that means it's in compression. And I spent a lot of time and I fumbled a little bit because I was sorting out signs, but boom, it gave me the answer. It gave me the sign. It gave me the, and so the system works. The system works. Now, if you want to go back in and calculate stresses, stress in the steel is equal to the force in the steel, 23.7 kip over area of the steel, which now at this point I remember 1.5 inches squared. We can calculate that. Stress in the steel, 18,960. The stress in the bronze, 19,000, just a little higher. Interesting, kind of interesting the way they posed that. Is there something else I was supposed to figure out? The vertical displacement of the bearing plate C. Well, we've got everything. We can just punch right back into that. And when you do that, you're going to get, well, I could do it a lot of different ways, but deflection in the steel, which is then going to be equal to how much the plate moves, is equal to PL over AE. And when I calculate that all out, it's going to be equal to 0.0454 inches is my last answer. So I had to get stresses. I got that. I had to get deflections. I got that. I'm even going with rainbow colored because that's so much fun. Follow the process. Follow the process. It will work for you. All right, don't worry. There's more coming.